Next, we take a look at ROV CMOL software's operational risk module. As usual, we started the CMOL software, the Credit Market Operational Liquidity ALM software application. And what I did was I loaded the example and went to the operational risk tab. So under operational risk, you would see three sub-tab levels. In this case, we see Basel Op Risk, the BIA, Basic Indicator Approach, TSA, the Standard Approach, ASA, Alternate Standard Approach, and RSA, the Revised Standardized Approach. So four of the basic approaches listed here in the first tab. Then in the second tab, we have the Basel OPCAR, Operational Capital at Risk methodology, which is part of the AMA, the Advanced Method Approach, and that pertains to Basel II and Basel III requirements. We also have the loss distribution using simulation AMA approach as well. So these two are competing approaches in the AMA, and we have both of these. And both methodologies apply something called distributional fitting, frequency distribution, and running something called convolution modeling. And we'll go into the convolution in a bit. So we'll get started with the Basel Op Risk, and because we loaded the example, you would see sample data that's preloaded in this case. Again, all of these input assumptions are white in color. Anything that is grayscaled, would be your calculated results. So for instance, the value here could be overwritten to anything that you want to, and calculate this automatically. Okay, so your capital charge using the BIA is computed automatically. You can also, as usual, do a copy-paste from Microsoft Excel. Okay, so if you're in Excel and you copy and pasted it, just use a Control-V to paste the data in automatically. So any input cells are white in color. You have the option to actually save your own data. So my example, for instance, after you've entered all this, and do a save as, and it will be listed down here, and you can rearrange it to whatever location that you wish. So we'll just load up a very simple example of sample 1, and notice that everything's calculated for you, your capital charge and also percentage of the capital charge based on your alpha, your beta levels, and so forth. So very, very simple to use. In the revised standardized approach, and by the way, the methodologies are explained in a little bit more detail when you go to File and you click on Help, and you see the user manual in there as well. That gives you a little bit more detail on the methodologies of each of the approaches. In the revised standard approach, typically we would separate everything up into BI categories or business indicator categories. We have the interest income, expenses, your fee income expense. These are all based on Basel 3 requirements. You have your business indicator and capital charge calculated automatically. The standard approach in Basel II, Basel III requires that you use euros as a basis for calculations, and therefore if you have this checkbox selected, we would use Basel III defaults, and the Basel III defaults are in thousands of euros, and here are the categories or buckets that are in Basel III. So anything from 0 to 100 1,000 in this case, to 1,000,000, and so forth and so on. And here are the beta coefficients that Basel requires you to use. However, there are different countries that might undergo certain regulatory compliance issues and central bank requirements, which might differ a little from Basel requirements. And this checkbox here, if you uncheck it, allows you to make modifications as necessary to the beta coefficients and also to the categories. And of course, you don't have to use euros. You can use pesos, dollars, you can use yen, and so forth, renminbi, and so forth. But in this example, we'll just use the Basel 3 defaults. So what you do is you enter in the data and it will be calculated for you. And just remember to keep saving the models. And once you save those models, again, we cannot stress strongly enough, make sure you go to the menu item and do a file save as. The save as saves it as an encrypted file and is a single unified file that saves all of the inputs from all of your credit, market, operational, liquidity, asset liability, analytical model tabs as a single unified encrypted file, okay, which includes all of your data sets here, as many data sets as you want. So very simple methodology. Now, let's go to the AMA methodology. There are two AMA methods here, loss distribution and the Basel OPCAR methods. So in your Basel OPCAR methodology, what we do is we start from left to right. We do a fitting, which means you give me some data that we can actually run some fitting on. And once it's fitted, you can also, by the way, skip the fitting if you don't want to and go directly into the setting of the assumptions, the convolution assumptions and the simulation assumptions, run the simulation and generate the results. So you go from left to right. In the loss severity fitting, what you typically do is you enter, historical losses, operational losses from various departments, divisions, business units, whatever you want to. And each of these columns will be a list of individual itemized losses. So in this case, it's $2,000, $2,908, or whatever the decimalization is. So whatever your decimals represent. So you use historical data losses for that, and you would, copy paste that data in. If you have the historical data. If you do not have historical data, you can use subject matter expert estimates, which is something that we'll go into in a second. And once you've done, the listing of the data, copy pasted this, what you do is you click on Run Distribution Fitting, and out comes your distributional fitting. The top 10 distributions are listed here: Gamma, Weibull, Gumbel Max, and so forth. And it's listed via p-value or probability value. In this case, for variable 2, we fitted variable 2 using this methodology called Kolmogorov-Smirnov. There are also alternate methodologies. All these are listed in the user manual. We highly recommend, if you're in doubt, to use the KS methodology. Kolmogorov-Smirnov is the most powerful. Select the variable that you're fitting. In this case, we're fitting Department 2's variable 2. And I clicked on Run Distributional Fitting, and the best fit in this case happened to be Gamma distribution. The second fit is Weibull, and so forth. If you click on Gamma, you see that Gamma uses 2 inputs. It uses an alpha and a beta. So the Gamma fitting gives you 1.9467 on alpha and beta of 1.1239. That's the best fit with a 93.12% probability of fit. So the accuracy is probably approximately 93%. This is based on actual historical data in this case. You can also see the actual versus the theoretical distributions, mean, median, standard deviation, skewness, kurtosis, and so forth. You can see how closely the actual versus the theoretical matches. Actual just means the actual of Department 2, the actual data here. The average is 2.19. The theoretical fit is 2.1879, close enough to 2.19, using these alpha and beta estimates. The medians, the standard deviation, how close they are from one to the other. What it does is the fitting tries to fit all of them simultaneously. So it doesn't just pick one versus, the rest of the other distributions, distributional means and moments. Clearly, we would choose the best one. And if you're interested, you can go select the best fitting distribution and paste fitted parameters to frequency severity tab. If you click that, what it will do is take your alpha and beta and find whatever distribution that's best fitting that you've selected and put those values in here, if you will. In this case, if we choose gamma and we click on paste, you would see a Poisson gamma. In this case, will be 1.19467 to 1.1239 in this case that we pasted back into this tab right here. Or you can alternatively utilize your own subject matter experts. If I choose SME in this case, let's just load a subject matter expert example. And SME just means if I don't have all the data. Previously, we have historical loss data where we have hundreds or thousands of data points. Then we will do a probability distribution. That clearly will provide you the best fitting data, best fitting distribution, and the best simulation. However, sometimes where you don't really have that information, we can use subject matter experts. So in an SME example, we can enter in percentiles or mean value. So let's just say the percentile is $12.5 million of losses, and that's the 10th percentile. The 85th percentile is, let's say, $25.3% million of losses. So using 2 of these percentiles, or it could be a percentile and a mean, all you need to do is obtain 2 data points, in this case $12.5 million and $25.3 million at the P10 or the 10th percentile and P85, the 85th percentile. That's all you need, and all you have to do at that point is run severity loss data fit, and it will tell you your R square of 100% clearly is the best fitting. Okay, the higher the R square, the higher the fit in this case. So it says that your log logistic fit is a really good fit, and the mean and the rho or the alpha value is 18.54. The beta or the standard deviation is 5.58. What these mean, these 2 columns, if you will, represent the parameters. For example, if you look at log normal distribution, and we go to log normal distribution uses a mean and a standard deviation, or mu and sigma. If we look at a gamma distribution, gamma we don't use mean or standard deviation, we use alpha or beta. If you go to an exponential distribution, we only use rho. which is the mean occurrence rate, or we just call it rho. So in this example, that's why we have alpha, mean, and rho. So if you look at exponential, you don't have anything else. There's only a single input, it's the rho input. If you look at log normal, we have these two inputs. We would use the mean and the standard deviation. That's just the naming convention, that's all. If you use the gamma distribution, it will be the alpha and the beta, because gamma uses alpha beta. It really doesn't matter. It just tells you this is your first parameter and this is your second parameter. So we have the first parameter, second parameters, first parameter, second parameter, and so forth. So it tells you whatever the best fit is. You choose whichever distribution you would like to use in this case. That's how we obtain these example inputs in this case. So we will go to the frequency and severity assumptions under the AMA OPCAR method. And in here we say Poisson distribution, which is the frequency. It's frequency and severity. So frequency just tells you how frequently something actually occurs within a 1 month, 1 year period, whatever your time period is. Okay. And severity tells you how much, what the dollar amount or the peso amount or the numerical amount of each of those on average. What is the, on average, when an error or a risk actually occurs, how much is the impact? So we have a frequency, we have an impact. We take frequency, we multiply by impact, we get the loss distribution or loss distribution analysis, if you will. And we can calculate that using convolution and or simulation, or combination of both things. So convolution of two distributions or running a Monte Carlo simulation on that. So in here, the Poisson tells you, well, come up with an OPCAR value at risk. So typical VAR is 99.9% or 99.95%. So enter whatever value that makes sense for you. And the Poisson here tells you what is the frequency for that time period, whether you're looking at monthly or annual data. What is the frequency of occurrence? So let's say in this case there are 30 instances of this particular type of risk for this department. Then what we do is we go into all the compound distributions. So compound Poisson exponential, compound Poisson Frechet, compound Poisson gamma, and so forth. So Poisson is the frequency, and the next distribution, exponential, Frechet, gamma, logistic, all those things are your impact or your severity distribution. So we take your impact multiplied by severity to get the output. So in this case, you can put in your own data if you know what the alpha and betas are. If you don't, do what we just did previously. We can use subject matter experts to enter in these percentiles and getting the best fit, or using historical data to provide the best fit for you if you don't know what the actual alpha and betas and all the settings are. As usual, you can save as many models as you want on here. So in this case, we'll just resurrect this example model that we had previously, that we had set up previously. And in this example, you can run convolution or not. If you run a convolution, it might take an extra couple minutes or a couple additional seconds. What convolution does is it takes the two distributions, probability distributions, and analytically and mathematically compute it without using simulation. If you don't select this, it will run a little bit faster. It will only run the simulation piece. So for example, I'll click convolute and simulate. Notice what's happening at the bottom here on the bottom left. It tells you that simulating. In this case, we asked it to simulate 10,000 trials. So it's going through 10,000 iterations. And there you have it. That's your result. And also, we have a seed value as an FYI. If you do not input a seed value, it will randomly generate a seed value for you. If you put in a seed value, what happens is it will generate the exact same distribution, same exact results for you every single time, assuming that the inputs are exactly the same. So it's really helpful to put a seed value. That way you can generate, same results so that you can compare them over time, if you will. So here's the convoluted simulation results. We asked for 99.9%. Of course, you can make a change to left tail, right tail, modify it to whatever percentile that you want. Just enter in the value and hit tab on your keyboard. Tab just leaves the cell and it tells the software that you have made an input in this case. And here you would see various distributions: compound, exponential, gamma, Frechet, log normal, and so forth. You can choose the distribution that you're interested in, and that makes sense for you. And here you would see simulated expected loss distribution, frequency and severity. So frequency is your Poisson distribution. Severity in this case happens to be the gamma distribution. And what you do is and by the way, you multiply your frequency with your severity, and you would get your loss distribution. You can also make changes to the chart if you want to, copy, paste, save it, open a previously visible chart, expand this however you want to see the visualization. On the right-hand side is where your results are. It tells you your simulated value with a left tail of 99.9% is $505.95 million in this case. So we have your frequency, severity, and loss distribution. This is what we're looking at. So left tail 99.9% is 505 million. You can look at the mean is 106 million. You can see your simulated expected losses versus convolution of expected losses is 106 million. They actually match very nicely. The 99.9% simulated OPCAR, your value at risk, your capital at risk, is $505 million. And if you use convolution, that matches to 99.47%. We asked for 99.9%, so that's close enough because we've only generated 10,000 simulation trials, and these two methodologies, tend to converge at the same answer when we have a lot of simulation trials. But in this case, in both methodologies, 99.9, 99.5, that's pretty close to each other, and therefore we feel very confident with the results, and so we can use 505.95 as the simulated OPCAR. And so the delta, the difference between simulated OPCAR and your expected losses is your unexpected losses, is your additional capital that is required, economic capital of $399 million in this case. So everything is visible here. You can look at all the other mean, median, standard deviation, skewness, and so forth, evaluations of the simulation. If you selected run convolution models, what happens is this value will be calculated. The not applicable will be computed because we asked it to do the convolution. And instead of giving you a percentile, it will give you an actual dollar amount, whether it's 505, 506 million, or $507 million. That takes an extra minute or two typically to compute. Okay, so that's your Basel OPCAR AMA methodology. Now we go to the loss distribution AMA method. In the loss distribution analysis, very similar to Basel OPCAR, you do a loss data fitting, distribution of the fitting, and then we calculate the simulated losses. Same exact approach. The difference now is in how you set up data. So in the loss distribution analysis approach, what you do is you create multiple variables of columns in this case. The typical standard column is your risk type. Here I just intentionally call it ABC, MNO, XYZ. So we have 3 different risk types. These are business units or locations or whatever departments you want to look at. These are the actual losses. Each of these are different losses. So $5.7 million losses, XYZ, California. Next month, next period, next time index, XYZ had another loss in the state of California for $2.34 million. So these are all actual losses, if you will. And again, you can copy paste from Microsoft Excel. You can also put in a date index if you wish. Date index could be, in years, months, whatever the dates are. Okay, just as long as your index are, identifiable. So 8 and 8 here, 5 and 5, 2015, 2015, whatever you want to do. So you see that the data here is all categorized into various, categories, subcategories, as opposed to using the Basel OPCAR AMA approach, which is there is no categorization. It's just all the data. Here it is. Thank you very much. Run the fitting and run the simulation for me as is based on the data that I have. So this is raw data. This is categorized data in this case. So if you have categorized data, what you need to do is tell me what categorization we're looking at. So loss data is in variable 3 in this case. You select the variable we're looking at, so which are losses, the dollar amounts. Fit positive losses only, so ignore all the negative numbers. Segmentation of risk, so risk type is your segments, your XYZ, ABC, and so forth. Your segment by business lines, if you want to, by business unit. And of course, if you have if the data is from a single analysis or multiple periods. If it's multiple periods or multiple years, we would need to segregate them. We need to have a date index as well. So once you're done with this, again, as usual, save them and run the distribution. And notice that it's fitting all various segments, segment 1, 2, 3, 4, 5 in this case. MNO in New York, all of XYZ, all of ABC, all of MNO. Risk type XYZ in California only, and so forth. So here are all the business segments that you see, because in your data you have created the segmentation already. And here's the segments. choose whatever segment you want. You can override any of the data as required, run a simulation, and out comes your simulated results. And in the simulated losses AMA, you can select whatever segment or subsegment that you're looking at, and obtain the probability distribution of the simulated frequency and the severity. And the multiplication of frequency and severity, of course, is the expected loss distribution. You can also click on any of these input icons and you make modifications to the chart, expanding, extracting, and so forth, and look at the distributional results. And finally, you can click on the menu item and do a create report. And what happens is, once that's done, it will take approximately a minute or so to generate all the reports. And assuming that you have results on each of the tabs or subtabs, what you would see is a Microsoft Excel report that is being generated, which has all of your input assumptions, your data, charts, results, and so forth, where you can do a file save as and have yourself an archived report